Thanks for the introduction. My name is Ilden Dabowski. I'm a PhD student at the Technical University in Vienna and a researcher at SBA Research in Vienna. So for this talk, I'm gonna simplify, take file format, data formats, protocols, treat them all as a language. They are describing the data, and the file is a transmission, is a data stream, is one or more packets. Conceptually, from the LangSec point of view, they're quite the same. And when we look at the typical input path, we have some machine that takes the data, interprets it, decodes, parses it, does some computation, and outputs something that we like to see. Maybe it's a spreadsheet, maybe it's a picture, basically depending on the data that it was fed with. In the worst case, from the LangSec perspective, this machine is Turing complete. This is all just a part of the picture. Then usually these machines are nested, concatenated, or stacked in some way. For example, you could have like a very simple machine that is a synchronizer in front that detects where the data starts, and then you have some error correction or decompression, and then the final machine that reads your data and does something. There are different possibilities why we nest or layer the data and these machines. And in some cases, we have another simple machine in front of it that is a dissector, which classifies the data format and usually returns one path or one option how to read these data. This is very common since usually we'd like to have, or the nice thing about standards is that there are so many to choose from. So we have like the picture program has to be able to read multiple picture formats. And so we typically end up with an even more complex machine or array of machines. So let's talk about the dissector a little bit more. We can play tricks with the dissector by building binary polyglots. There is this tremendous work from Ange Albertini that uses different file formats like PDF, zip, and JPEG and stuff them so together that they're actually valid for all three file formats. And you can open it with different programs and it shows you different content. This has already security implications. The famous ambiguity is insecurity paradigm. Imagine an antivirus firewall that does not know how to treat this file, and it might treat this file as one type, scan for malicious content, but the user that opens the file treats it as another file. So let's picture this a little bit. We have our piece of data, and we carefully interleave these different file formats together, maybe even reusing some of the bytes for both, and some bytes are only for one or the other file format. The other thing I mentioned briefly before, one of these machines could be an error correcting machine. So an error correcting machine is something that is heavily used, for example, in data transmission or in storage. For example, digital radio broadcasts of different kinds, radio and video, in telephone networks with GSM, UMTS, Tetra, whatever you name, or with storage on hard disks, in RAIDs, in cloud computing, and also with barcodes as kind of in between transmission and storage. So forward error correction is basically a technique that cope with errors on an unreliable channel without having a return channel. And it uses some kind of redundant encoding. There are different types of these error correction techniques, very simple like parity and Hamming codes, or complex one with like Reed-Salomon or turbo codes. For this talk, we can treat them like a black box. They just correct our data within a certain margin, error margin that usually can be configured. So it transforms then data into code words and vice versa. As long as this error margin is not overstressed, we can, or the transmission channel or the errors can override parts of the data, usually almost everything except maybe for the ECC header itself and a synchronization signal in front. Basically, we can now stick both things together and include foreign or alien data into this data packet or file or transmission, because the error correction will transparently, for the one data stream, will transparently abstract the foreign data away. On the other hand, the foreign data is still in this packet. The difference to, let's say, the packet-in-packet attack from Travis Goodspeed et al. Is that in this case, we do not modify the user data. The user data after the error correction remains the same. We just included another packet inside of it, and both packets are actually correct. It's also not like a hidden data channel, because we can actually put in very valid data in there that is then correctly picked up by some decoder, by some standard compliant decoder. Sometimes we also include, these packets include a kind of byte sequence header or magic value or a marker or a synchronization pattern. And even that one we can include inside of this alien data. So these, as I told before, this is used in several transmission techniques like radio and storage or in storage. And it's also used in barcodes. So we put up a simple example based on barcodes. So you can So you can take one barcode and embed another barcode into it, and both are actually standard compliant, and it's based on the implementation of the reader, which one it will decode. So the nice thing about barcodes again is there are so many to choose from. We can stuff different barcode types into another, or we can stuff the same barcode type into it. This is just a quick overview about different 2D barcode types. We focused in our experiments on the barcodes with square pixels. So we picked up QR, data matrix, and ADSTAC codes and tested it with 13 decoders. The most popular multi-standard barcode readers for iPhone and Android, and a professional symbol barcode reader that is used like in point of sale installations. So just a quick few examples. Like in this one, we stuffed an ADSTAC code into a bigger QR code, and you can see some decode the inner barcode, some decode the outer barcode. Sometimes it's indifferent and they decode one or another based on pure chance. We did this with data matrix as well. You can see that, for example, Neo Reader only prefers the inner barcode, in this case the data matrix barcode. Other ones are either decoding the inner or the outer one. with this example of QR in QR. We can see that, for example, the symbol reader strongly prefers the inner one, while most other readers decode the outer one, or sometimes decode none, but it's highly implementation specific. And the implementation basically is as follows. We have one very computational lightweight machine that tries to find synchronization markers in the picture and determine which kind of barcode the user is scanning. And then we have a computational, more complex code that then decodes the data. And once chosen a path, then the decoder runs down and just returns one of these codes. So, yeah, and while the standard for a particular barcode, while they exist, there is no standard in a sequence how to dissect different barcodes. So is it just harmless fun, or are there some practical implications of it? With QR codes, we know there have been several vulnerabilities, like these USSD codes that can wipe your phone into and make a factory reset. They can generate premium rate SMS messages, or they can trigger exploits in the web browser. With the knowledge that some readers and some phones or some decoders prefer one code or another, I can actually distinguish between different platforms and readers, and then tailor exploits for specific users. Or maybe do just probabilistic exploits, like divert a small number of users to transfer money to a different location, since QR codes are also used like by PayPal and Bitcoin. So for the barcode domain, we can think of different countermeasures, like a stringent decoding order, or presenting the user with different options as soon as the reader software finds more than one code. But this would include that the reading software actually tries to decode all possible codes, regardless which one it found first. However, for the generic case, when we go back to the more generic transmission example from before, it's kind of hard to spot multiple synchronization markers in an asynchronous data channel and verify that they're belonging to non-overlapping data packets. And this might also include decoding and verifying all possible interpretations of the received data. So application specific, the decoder could either drop the data, or it can escalate it up towards the user and let the user choose. You could probably think also of other heuristics, like choosing the data stream that has the highest data density, but in either way, it's a kind of guessing, and ambiguity is insecurity. So to wrap things up, the main conceptual problem with countermeasures in this area is that ECCs, or error-correcting codes, are designed to transparently hide any modifications from the processing layers above. And as the host data as well as the parasitic data are actually valid and conform to specifications. So having in some application domains, a stringent language description that includes rules for dissecting multiple languages or standard might be a solution, but this will not work in the general case. So this was my talk, and I'm happy to take questions.
Let's thank our speaker. Questions? Yes, Jacob.
Would you say this is somewhat analogous to the rowhammer bug, where you have closer to the phi level a ambiguity that's that's propagating through and actually creating an application layer vulnerability?
You can definitely see it this way, yeah.
Thank you.
Anybody else?